So this is the content, okay? I will set up the framework and I'll outline why one may conjecture that in, nice to see you. Hello. Why you get uniqueness in linear quadratic dynamics. However, to kill this conjecture, there are two counterexamples in the literature. One is by Werder and an older one is by Locke. Given these counterexamples, I'll opt for a general analysis of economic models in one state, either a capital stock or a resource. And to give you already an idea with some caveats, I somehow confirm my conjecture that in economic models, you get uniqueness, okay? But now comes another counterexample, because if you go for high-dimensional state spaces, you can get in perfectly economically meaningful models, you can get multiple linear Markov perfect equilibrium. So we all know that if you look for nonlinear strategies, you always have infinitely many. But if you look to hundreds of economic papers with one state in particular, the linear Markov perfect equilibrium is unique. Okay? Okay. So I'll set up, I think this is familiar stuff to everyone. We have a dynamic game here formulated for M players. And then, of course, in order to determine Markov perfect equilibria, we have to solve the Hamilton-Jacobi-Bellman equation. And the focus of this investigation is on linear Markov perfect and important symmetric equilibria. Okay? So now I come to a geometrical analysis of one state problem. Namely, you have one state, a scalar control, and I use phase prime analysis of the symmetric game. So let me use the laser pointer. So you know this is the objective. Then you get, by the maximizing condition, the optimal control. You can substitute this control, and then you can determine the dynamics. So you get, crucially, by making this phase plane analysis, you get three crucial loads. Okay? So you get in the xv prime plane, you can differentiate this differential equation once more, and then you can characterize the optimal strategy as a ratio of two linear, or more precise, linear terms, P and Q, okay? So if we have a linear strategy, of course, the value function must be quadratic. So I call subsequently V prime a strategy, although we know the strategy UI will be a function, a linear function of V prime, okay? So now look at this differential equation. We have two crucial loads here. One is where the derivative is 0, which is P equal to 0. There's another crucial locus where the function has a singularity. So in this case, this is Q is equal to 0. And now the crucial feature is a linear strategy must pass through this intersection of P equal to 0 to Q equal to 0. Otherwise, no linear strategy exists, okay? And there's a third crucial locus, which I mentioned already, is the steady state line, which can also be expressed as an affine function of x. No? So V prime is an affine function of x, which is in this chart, the green line. No? So by the nature of the problem, you get two roots for the quadratic term or the linear term in V prime. And the important proposition is, which holds in all these games, in a linear Markov perfect equilibrium, v double prime, which is the coefficient of the value function v2, must be less than the slope of the steady state line. Okay? So this is an important proposition in this case. Only the solution passing through this intersection, which has a slope less than the steady state line, qualifies for a linear Markov perfect equilibrium. So if you look at this chart, you see immediately that this leaves of the two potential candidates only the red line as a linear Markov perfect equilibrium, because the blue line violates the condition. You see immediately why this is. First of all, the steady state would be the negative domain, and you would run away. So it would diverge. So it would not satisfy the transitionality condition. So the crucial condition that you should remember is the following, that the second derivative of the value function must be less than the slope of the steady state. This character. In the normalized coordinate system, these two solutions would be even orthogonal. Now, from this, you immediately obtain the conjecture that an LMPE is unique, at least if the state is one-dimensional. And this conjecture seems to be confirmed in hundreds, I'm not exaggerating, in hundreds of papers. However, there are two counterexamples. Okay? One is Engwerder, and the other is Lockwood. I will describe these examples subsequently. So in order to analyze this more clearly, I write down a very general linear quadratic objective function. So we include all linear, all first order, all second order terms in the objective. And the differential equation, which is the small f, is just linear. Okay? So we make here one assumption, which essentially is the Legendre-Klebsch necessary optimality condition from the cooperative optimization problem. Okay, so this is a very innocuous assumption. We just postulate that in the cooperative solution, the objective is concave with respect to the control. Okay, so if we apply now proposition 1, we must get that both solutions for the quadratic term of the value function must be less than the slope of the steady state line. The slope of the steady state line is given here explicitly on the right-hand side. Okay? So this is the criteria. This is a little bit boring because you have a lot of coefficients in the game, but
Franz, may I briefly interrupt you?
Yeah.
Why you have not a more general form of small f? We have a lot of models where you have here interaction between x and u in the system dynamics.
But for linear quadratic, the differential equation must be linear. There cannot be any interaction.
Yeah. So
I
you
can
see
have interaction in the second order terms in the objective.
You see no way to extend this theory to, let's say, if you have a term x times u.
In some sense, one could extend this, you're right. You could even apply the phase plane diagram that I've shown before. Yeah? The problem is you do not have a linear strategy anymore. It will be nonlinear, but you still get the counterpart that the solution must be singular. It must pass through the intersection. Let me go back. If you make this more general, you have a nonlinear differential equation, then you can still apply the analysis as it's here. The only difference is that P equal to 0 and Q is equal to 0 and S dot is equal to 0 will not be any more straight lines, but you still get the result that the singular Markov perfect equilibrium must pass through the intersection with P and Q equal to 0. And in fact, I've done this in special cases, for example, where I have hyperbolic absolute risk aversion. Okay, so this could be done, but our focus here, it's already complicated enough, at least for me, on linear quadratic games. Okay.
Thank you.
Okay. So now counterexamples. Okay, the first counterexample is the one of Englert, and you see what it does is you have the X-dots dynamic, you have the A1 is negative, so the objective is of both players is to drive the state X to 0, incurring the cost C4. So C4 is negative because it's costs. And C1 is the evaluation of the state. Okay, so in this example, we can compute the second order, the coefficient of the second order term of the value function. And below on the left-hand side, I plot a bifurcation diagram. No? So you see, as expected, as long as C1 is negative, which in this case means that the objective is strictly concave, of course, the equilibrium is unique. So recall, a candidate for a linear Markov perfect equilibrium must be such that the value V2, which is the second order, the coefficient of the second order term in the value function, must be less than the slope of the steady state line, which is here constant to 3. Okay, so you get immediately two solutions, but only one qualifies for an LMP. Okay, as you increase C1, so now you enter the convex domain in the objective, it's still unique. Only if you cross the point where C1 is greater than 9/4, so it's larger than 2, you get the two linear Markov perfect equilibria that also Englert reports. Okay? Now you could say, okay, you have now two linear Markov perfect equilibria, but immediately from economic perspective, you get this is nonsense because you only get these two LMPEs if the cooperative solution does not exist. You need such a strong convexity that the cooperative solution does not exist. And by not existing, I do not mean any subtlety about sufficient conditions or something like that. It's simply that the route that you have to take to compute the coefficient V2 would be imaginary, would be complex. Okay, so yes, we have a counterexample, but from an economic perspective, it's useless because it would presuppose that the cooperative solution does not exist. Okay, let us cut. So you can do this in the phase plan that I've shown at the beginning, but I skipped this. Let us come to the second example, Lockwood. Okay, so Lockwood has here, see the C1 as in Englert is negative. So Lockwood has a strictly concave objective, where because all these coefficients are negative, the differential equation is fairly similar to Englert. We want to drive the state to the origin. Okay. Again, we can compute the coefficient of the second order term. And again, I use a bifurcation diagram. From before, you know that only a coefficient V2, which is less than the slope of S prime, qualifies for qualifies for a linear Markov perfect equilibrium. So you get for C5, which is this cross term, if C5 is sufficiently positive, you get multiple equilibria, but I'll skip this domain. First of all, Lockwood doesn't include it. And again, in this domain, you fall into the trap of Englert that the cooperative solution would be convex in the control rather than concave in the control. So in this case, you would not maximize rather than minimize. So I focus here on the negative values of C5. And then you see again, for sufficiently negative values of C5, you get two linear Markov perfect equilibria. But note now, the crucial threshold in this example is that C5 must be less than minus 3/2. Okay? So what does this mean? You know, the own action of the player I enters here with the weight 1/2. So in order to get multiple equilibria in the Lockwood example, you need at least that C5, the impact of the competitor is minus 3/2. So it means at least 3 times larger than the own effect. So again, this is outright ridiculous in all economic examples that I know, because it assumes that the tail must wag the dog. But in all economic examples I know, you always assume that the own effect dominates the cross effect. So again, we have a second example, in this case due to Lockwood, but its economic implication content is, again, it cannot apply to economic models. Okay? So in this case, still my original conjecture is held up in spite of these two counterexamples. So now it's getting a little bit cumbersome because we make now the general analysis. I repeat for you on top all the coefficients. You don't have to memorize them. I still repeat the proposition, which means that V double prime, which is the coefficient V2, must be less than the slope of the steady state line. So if you substitute all these terms, you get this expression. Okay, so in this case, for multiple equilibria, for both solutions, whether you take plus or minus of the root, must be non-negative. Okay, because the term in front is positive because numerator and denominator are both negative. The numerator is negative by assumption of the Legendre-Krebs condition, and the denominator is negative, at least if we rule out that the tail wags the dog. Okay? So maybe since I put this as a remark at the end, neither the linear terms of the objective nor the intercept of the state equation enters the above stability criteria. Okay? Okay. So we continue. So if we have two or multiple linear Markov perfect equilibria, applying this term with the negative, adding the negative of the root, must this still be positive. We add here plus the root, then of course this term will be positive a fortiori. Okay? So if this term is positive, okay, we can move square root d to the right-hand side. Right-hand side and left-hand side are both positive. Okay, we can square and rearrange this and obtain this term. Okay? So again, the term in front of the square brackets must be positive, so we can focus on the term within the square brackets, which is repeated below. Okay? So you see here, the first term is negative if I rule out n querdas root of a convex objective. So you see a lot, you see this term could help to turn this inequality positive, and similar the last term. So just looking at this, it seems that multiple linear Markov equilibria are possible beyond the economically meaningless cases of Lockwood and Vienna. Okay? So let us explore this a little further. So what is, aside from the assumption that I already used, that the cooperative solution must exist and that the tail must not wag the dog, what additional properties characterize economic models? And I state here 3. One is usually we operate in the non-negative state, at least at a steady state. The controls should also be non-negative, also with some caveat, at least at a steady state. But in most cases, the differential equation is autonomous. Okay? So what does this mean? This means that there are essentially for the dynamics 2 possibilities. If we set the intercept here 0. Either you get A1 positive and A2 negative to get a steady state which is positive in the state and in the control, or you take the opposite, A1 is negative and A2 is positive. So in the first case, if A1 is positive, we speak of a graph of a common stock. Famous examples are fishing and Ramsey's saving model. The second case is we have depreciation of a public stock, which we may call capital, and the applications could be from industrial organizations. So I look now in detail at the cases if we talk about the common stock. So A1 is positive. Then you see this is growing. Okay? So if you do this analysis, and if you assume a concave objective with respect to the state, and you exclude that the tail wags the dog, then you still can meet this condition above if you make C7 positive and sufficiently large. No? In economic terms, this means a positive contribution of the interaction between the own control and the state to player I's objective. Okay? And this is shown with an example below. So you see here, if C7 is small, you have unique equilibria. So in this case, it's the positive term, yeah, as the inequality is stated. If you make C7 sufficiently large, you get 2 and thus multiple linear Markov perfect equilibria. Now, this looks like, again, a refutation of my conjecture, but in some sense, it's still not the case, because look at the right-hand side, which is the phase diagram from the beginning. You have these 2 crucial loads, P is equal to 0, Q is equal to 0. Then we know the strategies must pass through this intersection. So we get 2 solutions, the blue one and the yellow one, and they must cross the steady state line at a slope which is less than a steady state line. So indeed, we get, as seen on the left-hand side, 2 solutions. One, the strategy A, you may call it, we get the positive x, but for the strategy B, you get not only a negative x, but you get a very large negative state. Again, it's difficult to reconcile this within an economic model. Okay? So, again, this is a little bit tedious. I cut a long story short. You can play around with the coefficients to render both steady states in the positive domain. You see this on the left-hand side. You have one steady state, which is very large, x is 50, and the other one is very small. But in order to do this, you must make a fishing or a forestry model such that you do not gain from harvesting, but you only gain from planting. You need a lot of absurd observations to settle the steady states in the positive orthot. Okay. Now we make the same story, and I'll save you here the details with depreciation of a capital stock. Again, by proper choice of an interaction term, now with respect to the competitor's contribution, you see C8 is here. You can get 2 linear Markov perfect equilibria. But again, you cannot get it in the proper domain. So summing up, yes, given this general analysis, yes, multiple LMPEs are possible in linear quadratic games in one state, but not in economic models, because multiplicity contradicts economics, either in assumptions, this applies to GERAD and Lockwood, or in the outcomes. This is in the two examples that I given to you, in which the second or the additional linear Markov perfect equilibria leads to economically meaningless outcomes. So again, taking a little bit of detour, you still may think that the original conjecture, at least confined to economic models, can be upheld, namely that you get uniqueness in linear Markov perfect. Now comes the really big caveat, namely the matters are different for larger state spaces. Okay? So let us consider larger state space. So let us see, the example that I give to you is learning by doing. And as maybe to all of you has already happened, you discover something by serendipity. We were not interested in looking for multiple linear Markov perfect equilibria. We were just a little bit annoyed by the many papers reported on learning by doing. In particular, this one by Reichenstein. Okay, so what Reichenstein and a lot of other people do is they plot the costs or the prices of certain products versus cumulative globally output. So in this case, if you're not familiar with learning by doing, the rule of thumb by learning by doing is the following 80-20 rule. Whenever you double output, your costs fall to 80% or are reduced by 20%. Okay? So you know it's a power function. This is scale invariant in price round. Okay? So what these people do is they plot here the costs for photovoltaic modules against the globally cumulative production of photovoltaic modules. Okay? And then, of course, you may argue, can this learning by doing? How can the German, now bankrupt photovoltaic panel producers learn by what the Chinese produce? So this is, if this is the case, then there must be very strong spillovers. But if there are strong spillovers, then you somehow face the tragedy of the commons, because then you would have you could have an interest that your competitor is doing the costly first PV modules, and then you jump later onto the bandwagon. No? So somehow this is strange to us. And we thought, look, this is strange, or at least if you believe in this kind of charts, you need at least analyze the interplay between learning from own production and those of others, and the interaction in the goods market. And to account for this requires to account for dynamic and strategic interactions. Okay, this is how we started. And then we thought, okay, we set up a differential game, and we will somehow have a counter story to tell to all the people who make this simple chart, and this is how it started. Okay, so I'll describe now the learning by doing game. So you have here a choke price of 1. So this is the price. UI is what player I produces. UJ is what player J produces. It's set up here for 2 players, but in fact, we have done this for n players also. Then you subtract the cost. So this is the price minus cost between the bracket, and you multiply this by the production. Then this is your current flow of profits. Okay. And then you have learning. X is the state of knowledge. Your state of knowledge improves with your production, plus the spillover from what the other is producing. And then if you don't produce, you somehow lose your knowledge. Okay, so this is standard setup. The only difference to the standard learning by doing models is that in order to have a linear quadratic game, I assume a linear cost function. It's not the power function, but it's a linear cost function. But that's all. So the assumptions are more or less standard, but we can discuss it. First of all, the cost of the first unit must be below the choke price. The choke price is here. And second, the spillover must be imperfect. This is standard economic assumption. You learn more from what you do than what you learn from what the others do. Then we assume that the costs remain non-negative along the evolution and at the steady state. The price stays below the choke price, otherwise production would be negative. And this is now a crucial assumption. Both firms stay in the market. Just as a note, if you set the spillover perfect, which is you assume p is equal to 1, you end up with one state, and then it can be shown in the one-state world using our results from before, the outcome will be unique. So this looks a fairly innocuous, well-behaved differential game. The only peculiarity is that we have two states, or n states, if we have n players. And then you get, surprisingly, in the standard example, two strategies for the two players. So one is A. This is for the brown is for player 1, the blue is for the player 2. It's symmetric. And this is strategy B, here again, red and green. Okay. So they are different. And then you see the two solutions here to highlight the Markov perfection. I let player B start at a lower level of knowledge. Player 2 at the lower level of knowledge. Player 1 starts at the knowledge level of 1. And then you see for strategy B, a very fast convergence. So although the second player starts from behind, he catches up fairly fast. Note that this is important for the following analysis. Of course, by subcon perfection, even for strategy A, the player 2 must catch up, but you see the catching up is here very, very slow. Okay? And the same is here for the controls. Okay? So let us move to a bifurcation diagram. So let us start from the left. With no spillovers, I will come to this point afterwards, because first I focus on the multiple. So for intermediate spillovers, we have, so between spillovers between a little bit above 0.2 up to almost 0.4, we have multiple equilibria. Okay? So you see here, this is, if you want, the usual, the robust linear Markov perfect equilibrium, and this is the additional one. No? So if the spillover gets sufficient and large, this additional LMPE, linear Markov perfect equilibrium, loses its stability, or more precisely, the stability is restricted to the 45 degrees line, to symmetric solution. And this brings me back to the chart from before. You see that with this additional equilibrium, which is equilibrium A in the previous chart, you have an additional one, but as you increase the B, the convergence takes longer and longer until it vanishes. Okay? So we get a rather modest window of multiple equilibria, and then up to B is equal to 1, you get the standard linear Markov perfect equilibrium.
I have a question. Hello, I have a question. So here in the learning by doing, your cost is decreasing with respect to only your own state, not with respect to the other player's state.
Yeah, that's right.
Yeah. And what do we mean by spillover? I couldn't follow. Like,
yeah,
where is
I
it?
Go back, yes.
Yes.
So here you go to the learning, you see?
Okay.
X is the stock of, is your knowledge. You learn by your own production, and somehow you profit also from the production of your competitor.
Okay, but your cost doesn't decrease explicitly.
Oh, yes. By what the, when I produce, my knowledge increases. If you produce, my knowledge also increases. Not by that much. Okay, is this clear?
Yeah, thank you.
No, thank you. So now I come to, which is, now I focus on this mathematical and theoretical aspect, but from economic aspect, the other is even more important, because if the spillover is weak, okay, no LMPE exists, okay? Although the monopoly solution exists, the cartel solution, which is different, exists also. The open loop Nash equilibrium exists, they all exist, but the Markov perfect equilibrium does not exist. No? And the economic intuition is, in this case, with no spillovers. And if you start from behind, there is no sense for you to try to catch a gap. So in this sense, in an economic sense, this is a very negative result, because if learning by doing is going on in this kind of business, if the spillover is not large, there is no, at least economically robust equilibrium. And in this example, even if you go from 2 to 3 firms, the Markov perfect equilibrium also vanishes. So there, I think I summarize it anyway in the next slide. Okay? So the results from this learning by doing games is the following. First, and this is some of the focus of my presentation, it need not, the LMPE need not be unique in sensible economic models with a state space greater or equal to 2. This is a strong contrast to one-state models which dominate the literature, because in the ones, at least I was unable to find an economically meaningful example where I have 2 or multiple linear Markov perfect equilibrium. So the long run outcomes differ. The additional LMPE exists only over a particular parameter range and is more aggressive, which means it leads to higher outputs and more learning. However, and this is already mentioned, the economically less optimistic result, a Markov perfect equilibrium did not exist, although the open loop, cartel, monopoly solutions exist. And of course, and the competition is only feasible with proper or sufficiently large spillovers and for very few firms. So, as already mentioned in the previous example, there's no LMPE for any greater 2. And then, of course, if you speak of perfect competition, it's of course incompatible with learning by doing. Okay. So any question here before I come to other examples?
Yes, Franz, Fuad speaking. Hi, how are you?
Hi, nice to see you.
Nice to see you too. I have a question. I still don't know whether, I mean, I already saw your presentation in this conference, but still I'm not, sure that I got the message. Are we talking about multiple competing equilibria with different basins of attractions, or are we talking with with history dependency? Or are we talking about competing simultaneous equilibria, and then you need to find maybe some coordination among the players not to be trapped in the worst case steady state?
So let me answer. It's the second. If you have a one-state differential game, we all know in most examples you can generate a family of infinitely many nonlinear equilibria. So in this case, you have one game, and we restrict to linear strategy, and there are 2 over the whole state space. There's no basin of attraction. It's the whole state space which applies for each of these 2 strategies. And as you mentioned, if there are these two equilibria, usually the question arises, how to coordinate on these two equilibria?
Oh, because in the literature, you recently, since there is history dependency emerged as a possible case, although in specific models where you have actually history dependency with linear Markov perfect equilibrium. I'm referring to papers by Dockner and Wagner in 2014, to also David and his co-authors in 2017 on a R&D competitive model. So some papers show that this might happen also.
Yeah, but they have nonlinear games and nonlinear strategies. With linear strategies, this is not possible.
Yes, maybe more, because we have maybe more than one dimensional, more than one dimension of the game. Actually, that's why this is possible that emerges with linear strategies. I mean.
Yeah, but the Dockner-Wagner paper, they're all one-dimensional.
The what? The David?
The Dockner-Wagner, they assume
Dockner-Wagner, yes,
they
there
make
was
the
one.
auxiliary system, and this must be one-dimensional. Otherwise, they
use nonlinear strategy.
Yes, they use nonlinear strategy.
Okay.
I propose that you proceed.
It's one state. Okay. Okay. The other examples coming to this, a usual suspect is, because of it's fairly related, is the Reynolds models of capacity expansion. It's sketched here. I amend that for the difference that I allow for imperfect substitute of the complements. So the price is 1 minus all production minus S times the other production. And then if S is positive, then we have a substitute, and if S is negative, we have complements. No? To cut a long story short, again, in this example, in the Reynolds case, even for this extension, the outcome is still unique. Okay. Now, one way, and again, staying in the learning by doing case, it's no surprise, we can again generate multiple linear Markov equilibria. So to repeat, the objective is essentially as before. This is the price. 1 is the choke price, all production minus the competitor's production minus the cost. So this is the profit per unit multiplied by the units that you produce is the profit within the period. And now it's different from before, that the stock of knowledge, of own knowledge, increases only with your own production. But now, as the colleague mentioned before, the spillover takes place at the state level. So in this case, my costs are increased by my own stock of knowledge, but also by the stock of knowledge that the competitor has acquired. So this is somehow just another version of the learning by doing game. And for this reason, it's not so much surprising that we get multiple linear Markov perfect. Okay. So I save you this list because I was looking what is so specific about this learning by doing game. And maybe it's helpful, but I didn't think. Anyhow, be encouraged by this finding of multiple linear Markov perfect equilibria in an economically meaningful setting. We thought we should find other settings where we can generate this, if you want, new or surprising result. And somehow we did, at least, let's put the blame on me, I did not succeed very much. One example I can show you where I do get again multiple linear Markov perfect equilibria with the difference is now is we have two controls. Okay, so the objective here is the same. 1 minus the production is determines the price. This is the cost of player I. So this is the revenue per, the profit per unit. This is then the profit, and we subtract costs. So there are two controls. One control is the production, which is here, and the second is the investment AI. And the investment AI improves your knowledge. So in this case, it's not learning by doing, which drives your knowledge, but it's your investment that allows you to enhance your knowledge. Okay? And in this case, we can reduce the costs as we expand our stock of knowledge. We can reduce the cost from K by the parameter gamma times xi. So in this case, the firms have two controls. One is to produce, and the second to invest in order to reduce future costs of production. And in this example, I also do get multiple equilibria. That's so far. Okay? So I'll come to summarize. What did I try to tell you here is we address the in my opinion, by and large ignored possibility of multiple and symmetric linear Markov perfect equilibria in linear quadratic dynamic games, while the possibility of infinitely many nonlinear Markov perfect equilibria is extensively analyzed. Yeah? The so far given examples in the literature of Wirl, who uses absurdly strong convexity, and Lockwood, who needs that the tail wags the dog, violate economic assumption. So given these counterexamples to my conjecture, I tried to derive criteria for multiple linear Markov perfect equilibria in a general linear quadratic and symmetric differential games, admittedly at this stage confined to 2 players, which I think is not that crucial, but of course confined to 1 state, which is crucial because of the numbers of parameters that would otherwise be involved. Okay. Although the large set of parameters leads to a rather complicated and cumbersome criterion, I'm able to derive 2 additional routes to potentially multiple linear Markov perfect equilibria, namely an interaction between the player's controls and the state. Okay? To the existing ones that I've already mentioned, them, the strong convexity in the state or the tail wags the dog. However, all these additional examples in 1-state problems remain, in my opinion, arithmetically because all the above 4 pathways contradict economics, either in the assumptions or in the outcomes. So, contrary to the finding in the one-dimensional state space, we find multiple linear Markov perfect equilibria in a real-world, straightforward economic problem, in this case learning by doing, which requires, of course, a higher state space. So this suggests, so possible options for future research are that one checks other higher dimensional economic models, whether they allow for multiple linear Markov perfect equilibria. Another possible extension for future research has come to my mind from the discussion during this presentation, that one may look for 1-state nonlinear dynamic differential games, and whether one can use phase spread analysis in order to characterize the possibility of multiple. In this case, we must clarify singular Markov perfect equilibria. These are equilibria which pass through the intersection of P equal to Q, because otherwise we know already that there may be many nonlinear genuine, or the non-singular, in this case, Markov perfect equilibrium present. Okay, this brings me to the end. Thank you for your attention.